Hi, thank you for the introduction. So, the overarching motivation of this work is to think about the problem that we have in real time graphics programming, where we have a really strict divide between host code and GPU code. And so in real-time rendering, we generally have some code written on GPU platforms or to run on GPU platforms and some highly parallel rendering calculations, generally written in a special purpose shading language like GLSL or HLSL. And then we also have some corresponding host code that sets up and invokes this rendering work, including choosing which bits of GPU code to invoke and passing parameters to the GPU and other kinds of communication and coordination between the host and the GPU code. And this is generally written in some general purpose systems language like C++. And in the real-time graphics APIs, there's this really strict divide between these two portions of code, which results in a lot of pain points like subtle bugs if these two halves of code are not kept in sync with each other, which is really a manual process that the programmers are responsible for. And so instead, what I think we really want is a unified programming model for real-time graphics. And in these so-called unified environments, host and GPU code can be in the same programming language, same file, and same lexical scope. And they come with some inherent benefits, such as being able to just share types and functions between host code and GPU code and certain compatibility guarantees as well. We can communicate between them using proper variables. We don't have any of these magic number binding points. And we can also be guaranteed that type layouts are the same. But unfortunately, none of the real time graphics APIs provide any kind of unified environment. But in the GPU compute space, unified systems are really the standard with things like CUDA and SYCL. And so you may be wondering, can't real time graphics just use CUDA and SYCL? Yes. Thank you for coming to my talk. You've been a really great audience. Okay, well, not really. And there are multiple reasons why graphics just can't use any of these existing systems. And in this work, we focused on one in particular, which is the lack of adequate support for GPU shader code specialization. So, what exactly is that? Let's look at an example. So let's say that we have a scene with three different types of materials that need to use different pieces of code to calculate their final rendered color. And so we might have some standard material that we're going to use for most objects, but then we also have some special materials specifically for skin and cloth. And along with the material specific shader code, we also have just a bunch of other complex code that we need to run in the shader in order to calculate the pixel's color. And lots of hand waving about exactly what that is. But basically, we need to be able to slot in the material specific code at the appropriate place in the shader. And to get the best performance, what shader programmers typically do is to express these specialization options as static compile time branches. And so these will be evaluated when we compile the shader depending on which type of material we've defined during compilation. And so we can generate a specialized shader variant just for the standard material, which results in a compiled shader that just contains the standard material code and strips out the code for the other two. Then we can do the same for the skin and the cloth material, resulting in three total compiled shader variants, each specialized for exactly one material. And so when we're rendering an object that uses the standard material, we don't pay any of the costs associated with these other materials, such as any sort of shared local memory usage or higher register pressures or any other negative costs. Then, when we're shading an object, we can choose the shader variant specific to the material of that object. And so now on the left is that corresponding host code, there's CPU code, that chooses which variant to invoke based on the runtime information of the scene being rendered. And if we compare the host code to the GPU shader code from a few slides ago, notice that the code in the GPU is using a compile time parameter to generate these different variants. But the host code really needs to use a runtime version of that same parameter since we don't know what material types are used until we actually go to render the scene at runtime. And that's really a key challenge with supporting unified shader specialization. Specialization parameters are compile time parameters in GPU code, but they're runtime parameters in host code. And in a non unified world, we can work around this as shown in those previous slides. But in a unified system where we want a singular definition of these parameters, that same parameter now needs to serve both a compile time and a runtime purpose. And some prior works have explored unified shader programming, including shader specialization. So, for example, BraidGL utilizes a programming language feature called static staging to express shader code and specializations. And our prior work on Celos uses these key set of language features called staged metaprogramming that are available in the Lua Terra language to enable unified shader systems, including specialization. However, neither BraidGL nor Luatera are widely used languages in real-time graphics, and more importantly, these key language features that these prior works rely on are not available in the widely used languages. And so what we wanted to ask is, can we bring the benefits of unified programming to today's shader programming systems in the near term? Can we meet these existing systems where they are instead of relying on some features that they just don't have access to? And so to that end, we have some goals and constraints that guided our efforts. So of course, we want to use a language that's widely used in real-time graphics, but more than that, we want to allow programmers to write code that really looks and feels familiar in that language. And so we really did minimize any changes to that language as much as possible. Because we're doing render real-time graphics, performance is obviously really important. And in contrast to many prior works, we want to make sure that our approach and implementation strategies are ones that modern applications could adopt in the near term. And finally, as mentioned earlier, I think these systems really need to have first-class support for shader specialization and composition in order to handle these compile time versus runtime dichotomy of specialization. Which brings me to the key insight of our work, which is that we can create such a unified system in an existing, widely used language by co-opting existing features of that language and implementing them with alternate semantics that are better suited to the domain of real-time graphics. And so by co-opting existing features, this allows us to repurpose language features that are maybe not suitable for GPU code, and instead use those to express GPU and graphic-specific semantics and optimizations. And also by reusing existing features, we don't have to add a bunch of new stuff to the language and then worry about how those new features might interact with the rest of the language. And so to demonstrate this, we created a unified shader unified shader system integrated into an existing game engine, specifically Unreal Engine 4. So UE4 is a really popular, widely used game engine, and in UE4, users can write GPU shader code in HLSL, and then for each HLSL entry point, users must also write a corresponding C++ host side class to manage the host side aspects of shader setup and invocation. So let's look at an example. On the left is some GPU shader code written in HLSL, and on the right, we have the corresponding host shader class written in C++. And on all these code examples throughout the talk, I'm not going to talk about the code in detail, but I'll just highlight a few key points. So we can see that we have things called uniform parameters, which are declared in both the GPU code and the host code. And it's really up to the users to keep these declarations in sync and make sure that any changes are applied to both parts of the code. I'll also briefly mention varying parameters. So in this compute shader case, only the GPU code needs to declare them. But for these other types of shaders, like vertex and pixel shaders, both host and GPU code need declarations for varying parameters. And looking at one specific uniform parameter for a second, I want to point out that host and GPU code don't share any types. And so we've declared a struct in the host code that must then be redeclared in the GPU code. So going back to the shader, we have also these specialization parameters, but we only declare them in the host code. But then they're actually then used in the GPU code. And so I'm going to omit a discussion of how this all works in UE4. But the point I want to make is that this is really easy to mess up. Like if I have a typo in the GPU code that uses a specialization parameter, I'm not going to get any sort of warning or error. And similarly, if there's a typo in the string name on the host side, I'm also not going to get any sort of diagnostic help on that. And also just forgetting to declare a parameter in the host code doesn't generate any diagnostics either. And so future readers of the code might be wondering whether that was intentionally omitted or if maybe that was a bug and it's supposed to be there. And I actually found myself in that exact situation. And then a very crucial but subtle point of these specialization parameters is that they must be compile time constant in GPU code, but then they're set by runtime values in host code. And so as mentioned before, this is okay in a system where the host and the GPU code are separate in separate languages and separate files, and the UE4 toolchain handles compilation and dispatch appropriately. But this becomes a real issue in unified systems that we have to figure out a way to deal with. And so by looking at this code, we've identified the required elements of the interface between host code and GPU code. We need to be able to express uniform, varying, and specialization parameters, as well as some sort of entry point function to kick off GPU execution. And I'm also going to claim that it's useful to be able to denote which other functions are GPU compatible. And so this allows host-only functions to use host-only features and vice versa. So now let's look at our unified shader design, both to see how we express these various elements and to see some of the benefits that the unified system provides. So here's an example of a shader in our unified system. And note that the left and the right parts of the slide are now both part of the same C++ class, all contained within one file. So just like UE4, shaders in our system are written as C++ classes, but in contrast, this class contains both host code and GPU code. And the various elements of the host GPU interface are expressed using C++ attributes, including the uniform and specialization parameters, as well as marking GPU compatible functions in the GPU code entry point. And because both host and GPU code are unified into the same C++ class, the programmer only needs to declare parameters once rather than needing separate declarations for the host and GPU code. And related to this, specialization parameters are now explicitly declared not only for host code, but also for GPU code. And so this enables the compiler to provide extra validation, such as catching this typo here as a compile time error rather than it causing just a subtle bug if it were only implicitly declared. And also, thanks to the unified design, types are shared between host and GPU code. And so the GPU code just uses that quality enum, and it can reference all the enum types directly as well. And lastly, remember that specialization parameters must be compile time constant in GPU code, but then must be set by runtime values in host code. And so we handle this difference by requiring that the specialization parameters are declared to include all of the possible options for those parameters as compile time constants. And then in the host code, the programmer is free to set those parameters using just regular old runtime values, and our system handles that difference. Now that we know what a shader looks like in this unified system, let's dive into some of the specific design decisions for our system. We've already covered some of them. So for starters, we use C++ as our programming language of choice. It is one of, if not the most widely used languages in real-time graphics, and it's a natural choice for our case because it's what UE4 uses. Similarly, UE4 already expresses host shader code as C++ classes, and so we do the same as our system, same in our system rather. However, unlike UE4, our unified shader classes contain both host code and GPU code. The last two design decisions are very much related to this minimize changes to the language idea. And so the first one we've already seen. We're going to co-opt C++ attributes to express elements of the host GPU interface. And so this attribute syntax is standard in C++ 11, but C++ does not provide any kind of support for user-controlled attributes. And also, the C++ compiler is free to ignore attributes that it doesn't understand. And so attributes are really not meant to change the semantics of the program, but in our case, ignoring these attributes will just result in an incorrect program. And so we're very much violating what the standard semantics of C++ attributes are supposed to do. And instead, we repurpose them for the needs of graphics programming. But even more so than these attributes, where our design really departs from standard C++ is our use of inheritance and virtual functions to implement shader specialization and composition. And you might be wondering, why do we need to co-opt anything for composition and specialization? Well, C++ really doesn't have what we need for the specialization optimization. It kind of has two main ways to compose together different classes. And so we could use just the standard inheritance and virtual functions functionality, but this leads to dynamic dispatch of function implementations through the virtual function table. In contrast, we could instead use C++ templates. All template parameters need to be specified at compile time, and so this leads to static dispatch of functions. And what I'll claim is that dynamic dispatch is better for host shader code, since we want to invoke this GPU rendering work based on runtime parameter values. But in GPU shader code, specialization is really important to achieve the best performance. And so we really want static dispatch of all functions on the GPU, but this leads to some problems for the host code. And so we have as this problem where neither of these options are suitable for unified shader code because the host code and the GPU code have different requirements. And so I hope it's kind of clear why virtual functions aren't a good solution in this case. But in case you don't believe me about templates, I've got some extra slides we can talk about. And so the solution that we came up with is to co-opt virtual functions in order to implement specialization. And so programmers author shader code using inheritance of virtual functions like normally would, but then the system will code-gen different GPU specializations based on the relevant subtypes. And so host code can then set parameters just as it normally would in C++, but under the hood, the system will invoke different specialized GPU code based on the runtime types. And so in effect, we get the best of both worlds, all while allowing programmers to express composition in a very C++ style. So to look at this visually, programmers write what looks similar to just regular virtual function calls. And then the system will generate devirtualized versions of these virtual functions for the GPU code. And it will also generate specialized GPU shader variants for shaders that use these virtualized functions. And so these programmers, this allows programmers to write regular looking C++ code for their shaders, but then that code gets transformed into an implementation that's better suited to GPU code, and our system handles dispatch appropriately under the hood. Just to briefly mention some of the implementation information. So we use a source-to-source translator built on top of Clang, but in a way that doesn't require modifying the Clang code base, which helps to limit implementation effort and maintenance costs. The translator walks the Clang AST to retrieve relevant info from user-written source code, and then it uses that info to generate HLSL for GPU code, including multiple shaders to turn dynamic dispatch into, in order to turn dynamic dispatch via virtual functions into static dispatch instead. And then for host code, it generates C++ and uses UE4's existing shader system under the hood. And so this really helps to facilitate ease of integration and adoption by making these unified shaders compatible with existing C++ code, with existing UE4 code. And I also want to point out that we could add support for other shading languages and other engines by writing additional backends. Our current implementation is specific to UE4, but our overall designs and ideas are not. So to evaluate our system, we rewrote some of UE4 shaders to use the unified system, and we ran the infiltrator demo using both the original shaders and our unified shaders. And as shown, the performance of our unified shaders is similar to the original UE4 versions. We don't really see any differences in performance. And in addition, we wanted to make sure that our abstractions don't lead to any excessive code bloat. And so, similarly, the lines of code counts are comparable as well. We do have some additional lines in our versions. Some of that is due to stylistic differences. Some of it is due to some minor code duplication. And in the end, yes, some of these additional lines are due to our abstractions. But we think that the trade-offs are worth it for having more robust, user-friendly code. As for limitations, our current implementation only supports compute shaders. These are an increasingly large portion of a modern game shader code, and they're sufficient to demonstrate the challenges we wanted to show. But we nevertheless don't support the other shader types at the moment. And similarly, our translator only supports UE4's global shaders, which are shaders that don't need to interface with the mesh or material systems. And so to wrap up, we added unified shader programming to C++ by co-opting its existing features and implementing them with alternate semantics. So we co-opt C++'s attributes to express elements of the host GPU interface, and we co-opt inheritance and virtual functions for shader specialization. And since we aren't adding new features to C++, we're just reusing existing ones, our system can maintain compatibility with future versions of C++. Our unified shaders achieve similar performance and code sizes compared to the original UE4 shaders. So as future work, I think it'd be interesting to try to co-opt features of another language for graphics programming, such as maybe using Rust's generics. I think it'd be also interesting to explore what kind of optimizations we can perform by giving the compiler a unified view of the code and more information with which to optimize. And I think maybe we can make these optimizations even more powerful if we developed programming models beyond just this separate shader per render pass thing that we typically use now. And to sort of expand on that a little bit, maybe we could write rendering code as one big integrated unit and then let the compiler choose how to split that up into different shader kernels. And so I think there could be some benefit from doing compile time analysis to figure this out. But then there's also some greater potential for incorporating runtime optimizations too, perhaps leveraging information in a render graph system. And I want to note that unified shader programming and specialization support is really a prerequisite for these future types of systems. And with that, I'd like to thank the many people who helped us and gave us feedback on this work, and also thank you to Intel Corporation and NVIDIA Corporation for financial support. And thank you for listening to my talk. We've got some source code available for our translator on GitHub, and I'll be happy to answer any questions.
Oh, thank you very much. So we have time for questions. Let's see if there's any in there at the moment.
Yeah, I think I see one at the top of the question board. Good.
So how does this system compare to other similar systems such as Slang or Circle C++ shaders?
Yeah, so regarding slang, one kind of point is that it's not really what I would consider a unified language, since it really only is for the GPU part of shader code. And maybe they'll do something like that in the future. But one critical design element of slang is its use of the slang style generics and I forgot the name of it. but slang-style generics and interfaces, that's the word, which really that type of generic and interfaces aren't available in something like C++. And so I think if we were trying to apply the lessons of slang to C++, we would kind of have this mismatch in available features that we couldn't just use, translate those lessons directly. Regarding C++ Circle shaders, for those not familiar, Circle is a newer C++ compiler that adds a bunch of new features to C++, including some really interesting metaprogramming features. And it also has support for turning C++ into, I believe, GLSL, or maybe it's SPIR-V, so to compile C++ to shaders. And I think that's a really important prerequisite, is being able to translate C++ into GPU-compatible code. So they're doing that, which is awesome. But as far as the interface between hosts and GPUs, I think that their solution to that might involve a lot of these new fancy features that they're adding, which is departing a lot from standard C++. And so one of the contrasts of our goals is to say, how can we stick as close to regular old C++ as possible and just make minor changes instead of trying to add new stuff to Circle? And to be clear, I think Circle is really cool. I think we just kind of are coming at it from two different angles.
Okay. Well, I had a question. Well, actually, I mentioned this to a colleague who works in one of the other groups, and he was curious of, who do you feel is the main beneficiary of this? Is it someone who's working on the sort of like the engine software and providing a tool, or the actual game developer, or perhaps a poor person debugging the driver?
Definitely the first two, definitely. I haven't thought about the third one. But yeah, certainly the people actually writing the engine are writing a lot of shaders and writing a lot of shader code. And so they might be the ones both providing these tools and providing and, doing the implementation that I did, but for real in something like UE4 or Unity. But then the other people in that company working on that tools would also benefit by being able to have more robust code and not have to spend as much time debugging or dealing with minor compatibility errors that should really just be caught at compile time. And then also users of the engine who are creating their own games and might want to create their own shaders or their own rendering algorithms and things. Would also benefit then from, again, this increase in robustness while still being able to get equivalent performance. Debugging the driver is more interesting, because I think that's sort of, you've lowered, like, at least with our implementation, by the time it gets to the driver, you've stripped out all of that stuff. You've compiled down to the graphics APIs. You've compiled down to HLSL or GLSL or SPIR-V, and so I'm not sure if it would help with that as much, other than being able to eliminate those same compatibility challenges that you might have otherwise. So you can kind of eliminate a class of bugs, say it's not this problem because the system handles it for us.
Okay. Any other questions? Well, actually, I've just got one minor question. You gave some statistics with yours in terms of performance, and one of them was yours was slightly slower. Have you got any reasoning for that? Is there any specific feature that's missing?
No, I don't think so. I think this might just be minor variance when you run the same thing twice. Is kind of, I didn't see anything that was obviously different. The code, when we generate it, looks pretty similar. So yeah, I don't really have a satisfying explanation for you other than perhaps minor drift
Okay.
when you just run the same thing multiple times. Yeah.
Okay. Well, so since we don't have any other questions, shall we thank our presenter again?
Thank you.